Detecting dark matter and dark energy is like trying to find a silent, invisible elephant in a pitch-dark room using only the faintest vibrations on the floor. Together, these two mysterious forces make up 95% of the universe, yet we have never directly seen them. Dark matter accounts for about 27% of the cosmos, while dark energy makes up a staggering 68%, leaving only 5% for everything we know: stars, planets, atoms, and life itself. But if they are so dominant, why can't we detect them directly? And if they're real, how do we know they exist? Let's start with dark matter. Imagine spinning a toy car tied to a string. The faster you spin it, the more tension is needed to hold it in place. Galaxies spin at such high speeds that, according to Newtonian physics, they should fling apart, yet they don't. Something invisible is holding them together with extra gravity. That something is what we call dark matter. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. It also doesn't interact through the electromagnetic or strong nuclear forces, only gravity, and possibly the weak force. So, if dark matter is passing through us right now, which it likely is, at speeds of 220 km/s, why don't we feel it? Because it behaves more like a ghostly wind, moving through solid matter as if it weren't even there. Physicists suspect dark matter is made of unknown particles, perhaps WIMPs, weakly interacting massive particles, or axions. But experiments designed to catch dark matter in underground liquid xenon tanks, such as LuxZplin and XenonAunt, have yet to find conclusive evidence. Could it be that we're looking for the wrong thing? Some radical ideas suggest dark matter could be tiny black holes, exotic neutrinos, or even evidence of extra dimensions. What if dark matter isn't just another particle, but something fundamentally new, an entirely different kind of matter we haven't even conceived yet? Now, dark energy is even weirder. If dark matter pulls galaxies together, dark energy does the opposite. It pushes the universe apart. It's like an invisible hand stretching space itself, causing galaxies to drift away from each other at an accelerating rate. How do we know this? Observations of distant supernovae show that galaxies are receding faster over time, contradicting earlier theories that gravity should be slowing cosmic expansion. The only explanation is a repulsive force embedded within space itself, what we now call dark energy. But what is it? Is it vacuum energy, some unknown quantum field, or even a modification of gravity? One of the biggest puzzles is that quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than what we observe. A mismatch so absurd that physicists call it the worst prediction in history. Some theories propose that dark energy is a fifth force, an unknown fundamental interaction alongside gravity, electromagnetism, and the nuclear forces. But unlike the forces we know, dark energy is too weak to detect on Earth. If dark matter might be passing through your body right now, dark energy is even more elusive. It operates on cosmic scales, affecting the fate of the entire universe, but leaving no measurable trace in a lab. Could there be a deeper link between dark matter and dark energy? Are they two sides of the same cosmic mystery? Some physicists speculate that dark energy could be a changing field rather than a constant force, which might explain why the universe's expansion rate hasn't always been the same. Others suggest that our theories of gravity are incomplete. Perhaps what we call dark matter and dark energy are just signs that we don't fully understand how gravity works at the largest scales. The search for answers continues with new telescopes, underground detectors, and even quantum experiments pushing the boundaries of our knowledge. If we solve these mysteries, it could revolutionize physics, unlocking hidden forces, new particles, or even new dimensions of reality. Could dark matter hold the key to a new form of energy? Could dark energy reveal an unseen structure to the universe? If our physical world is our only structure, why is the universe so limited? Is it universal or just local? Or is there something even stranger lurking just beyond our current understanding? Dark matter is believed to constitute around 27% of the universe's total energy content, yet it remains undetectable by conventional methods. Unlike ordinary matter, which interacts via electromagnetic, weak and strong nuclear forces, dark matter is thought to interact only through gravity and possibly the weak nuclear force. This means that it neither emits nor reflects light, making it invisible to telescopes. Because of its lack of electromagnetic interaction, it does not form atoms or molecules, nor does it participate in chemical reactions, remaining a mysterious and ghostly component of the cosmos. The rotation curves of galaxies provide strong indirect evidence for dark matter. Spiral galaxies, like the Milky Way, rotate at speeds that should cause their outer regions to fly apart. However, the presence of an unseen mass, dark matter, gravitationally holds them together, explaining why they do not disintegrate despite their high rotational velocities. Imagine trying to detect wind in a completely dark room without feeling it. You wouldn't be able to see it or touch it, but you could infer its presence by observing objects moving unexpectedly, just as astronomers detect dark matter through its gravitational effects. So, several experimental efforts have been dedicated to detecting dark matter particles, particularly weakly interacting massive particles, WIMPs, and axions. Detectors are built deep underground to shield them from cosmic rays and background noise, using ultra-pure noble gases such as xenon or argon. The idea is that a dark matter particle may on rare occasions collide with an atomic nucleus, producing a detectable recoil. However, the interaction cross-section, the probability of such an interaction, is expected to be extremely low, making detection incredibly rare. Experiments like LuxZeplin, LZENONTON, use tanks of liquid xenon, where sensors are designed to pick up flashes of light when a particle collision occurs. Despite decades of research, no conclusive evidence for dark matter has yet been found. It's like waiting for a single raindrop to hit a grain of sand in a vast desert. Even if it happens, the chances of detecting it are slim without highly specialized instruments. While direct detection of dark matter remains elusive, astronomers infer its presence through gravitational lensing, a phenomenon where dark matter bends the path of light from distant galaxies. According to Einstein's general relativity, massive objects warp space-time, and light passing through these warped regions appears distorted. Observations of galaxy clusters have revealed that the amount of mass needed to create such distortions far exceeds the visible matter present, suggesting the existence of dark matter. The Bullet Cluster, a famous galaxy cluster collision, provided strong evidence for dark matter. When two clusters collided, their visible matter interacted and slowed down, but the majority of the gravitational mass, presumably dark matter, passed through undisturbed. Imagine shining a flashlight through a window with an invisible, distorted layer of glass. Even though you cannot see the glass itself, the way the light bends tells you that something is there. Dark energy, making up approximately 68% of the universe, is even more mysterious than dark matter. Unlike dark matter, which has gravitational attraction, dark energy appears to act in the opposite way, pushing space apart. It is responsible for the accelerating expansion of the universe, first confirmed through observations of Type A supernovae in the late 1990s. The leading hypothesis suggests that dark energy is an intrinsic property of space itself, often referred to as vacuum energy or the cosmological constant. However, its true nature remains unknown. Cosmic microwave background (CMB) studies and large-scale surveys of galaxy distributions have provided evidence that the universe's expansion rate is increasing, which can only be explained by the presence of dark energy. Think of dark energy like an invisible repelling force within a balloon that keeps inflating it faster and faster over time, even without any external air being added. Unlike dark matter, which might consist of particles, dark energy does not clump together or form structures. It behaves like a property of empty space. Its effects are only visible on cosmic scales and cannot be directly measured in a laboratory, while some experiments, such as vacuum energy measurements and atom interferometry, attempt to probe its existence, the effects are far too weak at small scales to provide conclusive results. The biggest theoretical challenge is that quantum field theory predicts vacuum energy to be vastly larger than what is observed, highlighting a major gap in our understanding of physics. Current research into dark energy focuses on studying the large-scale structure of the universe, including the clustering of galaxies and the evolution of cosmic expansion, using missions like the Euclid Telescope and the Vera C. Rubin Observatory. Dark energy is like the background hum of the universe. Its effects are only noticeable when looking at the vast cosmos over billions of years, rather than in a controlled experiment. If dark matter is made of WIMPs, axions, or sterile neutrinos, it should be present on Earth and throughout the galaxy, passing through us constantly. However, since it interacts weakly with normal matter, it does not accumulate in detectable amounts in everyday environments. Some experiments, such as cryogenic detectors and neutrino observatories, attempt to detect its presence, but so far no definitive signal has been observed. The Gran Sasso Laboratory in Italy and SNOLAB in Canada operate deep underground to minimize background noise and increase the chances of detecting a dark matter particle collision. Dark matter is like an invisible river flowing through us at all times, but since we are unable to interact with it, we don't even notice its presence. Dark matter and antimatter are fundamentally different. Antimatter consists of particles that have opposite charges compared to their matter counterparts, e.g. positrons for electrons, antiprotons for protons. When antimatter and matter meet, they annihilate each other in a burst of energy. If dark matter were antimatter, we would see enormous amounts of gamma rays from annihilation events. Since we do not observe such signals, dark matter is unlikely to be antimatter. Studies of high-energy cosmic rays and gamma-ray bursts have found no signs of large-scale dark matter annihilation events, suggesting that it does not behave like antimatter. If dark matter were antimatter, it would be like having invisible fireworks exploding everywhere in space. Since we don't see this happening, dark matter must be something else entirely. Several upcoming experiments aim to shed light on dark matter and dark energy. Next-generation dark matter detectors will be even more sensitive, and particle colliders like the Large Hadron Collider LHC are searching for new physics beyond the standard model that could explain dark matter particles. For dark energy, space-based telescopes will continue mapping the universe's expansion, searching for clues about its nature. Theoretical models, including modifications of gravity, are also being explored. The upcoming Vera C. Rubin Observatory will conduct a decade-long survey to track the movement of galaxies, helping to refine our understanding of dark energy's role in cosmic expansion. It's like searching for an unknown continent. Scientists have mapped the ocean and see its effects, but they haven't yet set foot on the new land to explore what's really there. Dark matter and dark energy remain two of the greatest mysteries in modern physics. While dark matter exerts gravitational pull and helps shape the structure of galaxies, dark energy drives the accelerated expansion of the universe. Both are invisible yet dominate the cosmos. The continued search for their true nature is at the frontier of scientific exploration and may lead to entirely new physics beyond our current understanding. Future discoveries about dark matter and dark energy could revolutionize our understanding of the fundamental forces governing the universe. Solving these mysteries is like uncovering the missing pages of a cosmic book. Without them, we only have a fraction of the full story.